Welcome back. Today is November the 18th, and we're going to finish up the last two chapters of the semester, and we're going to start at a random order here. So I'm going to begin with chapter 12 because it's easier to hit the most important topics of that. And then we're going to transition to chapter 11, which is the organometallic chapter. All right, so for chapter 12, we're going to study the mechanisms for radical reactions. I'm going to remove this. And so check this out. All right, so for a mechanism, every time you have a mechanism, basically what your aim is to go from point A to point B. So notice that here you could brominate in different carbons here of this propane. How many mono-bromo products can you make from propane? Monobromination products. 2, exactly right, because this carbon and that carbon will be equal, so that will be one opportunity or possibility, and then the other one will be right there. So you have 2 possibilities for monobromination. All right, so because this problem asks you to show the mechanism for the 2-bromo, so we're just interested in exchanging this H here with that bromo. All right, so all right, so let's begin here, the mechanism. So notice that for a mechanism on radicals, you have 3 stages: initiation, propagation, and termination. So I usually start off my radical chapter with this question: how do you call a Democrat that is free on bond? A free radical, right? All right, so let's get this reaction initiated. So you have a molecule of bromine, that's your first step. This molecule of bromine will be split in half by the help of light. So here you have light. This is light or energy. This is a photon of light, where H is Planck's constant and nu is your frequency. So energy, according to Einstein, is H times nu. All right? So you know that. This is also equals to, energy is equals to H lambda, I think, divided by C, something like that. Is that right? Or if the C goes on the top? I forgot. This might be right, or might be wrong, I don't know. But if I'm not sure, I'm just going to go with this one. That one I know. All right? Actually, I think I can figure it out. So C is equal to, what was that? Yeah, lambda. Yeah, lambda and nu. So, let's see, how does that work? Oh yeah, and so if I solve for nu, that would be equal to lambda divided by C. Yeah, so I had it right. So E is equal to H times lambda divided by C. All right, so that's all physics. All right, so yeah, that's correct now. All right, but this is it. This is what I'm interested in. So the light will come and split this bond here between these 2 bromines. So you have 2 electrons there when you apply light. And that's your initiator. This electron will come over here, and this other electron will come that way. All right? So when we're dealing with radical equations or reactions, we use half arrows. So this represents 1 electron. And when you have a full arrow, each part of the arrowhead represents 2 electrons. All right? So that's how you do it. And so when you split the bromine molecule, you get two Br radicals. All right? It has 7 electrons around it. And so that's your initiation. So this is the birth of the radical. So here the radical is born, then it's going to propagate. This is the life. This is the life of the radical. It's gonna marry, have kids. Why not have its offsprings? And so then it's gonna die. So this is the sad story. I call this the sad story of a radical reaction. It's gonna be terminated at the end. All right. So here's your radical Br. Now you have to get the product. So you're going to choose now the alkane that is going to give you product. So you're going to purposely choose the hydrogen on the second carbon. And you're going to exchange the electron. So this one electron goes and makes a bond there, and another electron goes there to the carbon. Wait. Like that. So now you have made HBr 1, 2, 3, 4, 5, 6, and then the 2 electrons here on this bond. That's 8, and you made one of the offsprings radicals. So it's now starting to propagate. Now this new radical is going to hang out with a new fresh molecule of bromine. And you don't need much. All you have to do is get one of the radicals initiated, and then the reaction will set off. So this is setting off the reaction. And so now you have this. You have made final product plus another radical of bromine that keeps propagating. See, this is an offspring of the initial. All right, so it keeps propagating, does it over and over and over until all the reaction gets completed. And then at the end of the molecule, you will have 3 options for termination steps. So you can have bromine, bromine. These are your options. Bromine, bromine. Like that. That's one, terminates. Or you can have alkyl radical with alkyl radical. Let's put a plus there. Oh, yeah. So here you have, this one goes like that. Then you have this. And then you will form, this is an undesired product. And finally, you can also have one last molecule of desired product form. And then you've made this. So there's no more. So you're making a covalent bond, and your reaction is complete. All right. So usually on a paper test, I ask my students, write the initiation, write the propagation steps, and write one termination step. And so they can pick, they usually choose one from these 3. All right. All right, so let's do the number 2. It says here, how many different dibromo derivatives can you expect from the synthesis of 2 moles of bromine with cyclohexane? Use stereochemistry to assign any possibility. All right, so before we do that one, let's practice with propane. So in propane, we learned that we have 1, 2 monobromination. How about dibrominations? How many options do you think we'll have for dibrominations? 3. Let's see if it's 3. 1, 2, 4. That's 4. Check this out. For dibromination, we'll have 1 here, 2 there. We will have a 1, 2, and a 1, 3. You see that? So that's what we're going to be doing on problem number 2. The different probabilities of doing mono or bisbromination. All right. So I said, how many different dibromo derivatives can you expect from the synthesis of 2 moles of bromine with cyclohexane? Use stereochemistry to assign any possibility. All right. So what we should do is, or what I usually do in a case like this, I'll make my cyclohexane. I'll make a few of them. And I'm going to start with the different combinations that I know. I'm going to start with 1, 1. Then I'm going to do 1, 2s, and then the 1, 3s, and then the 1, 4s if I can. All right. So I know that I'm going to have a bunch of them. So I'm going to start with the 1, 1. So with the 1, 1s, I have bromines, 1 bromine up, 1 bromine down. So this is a 1, 1. And that's the only one I have. All right. So for the 1, 2, I start with both up and 1 up, 1 down. Or 1 down, 1 up. All right, so this will be my 1, 2s. What happened to the 2 downs? You can just flip it. Yeah, that's exactly right. It'll be exactly the same as the original here. The 1, 2. That both are up. All right, so you cancel that one off. And then we have the 1, 3s. 1, 2, 3. So the 1, 3s will be 2 up. And notice that we'll have 3 combinations. 1 up, 1 down. And 1 down, 1 up. If you do 2 downs, I want you to know that this is the same thing as that. So just simply bring your spatula and flip that tortilla. Okay? So this will be the same thing as that one on the top. All right. And then, so this will be my 1, 3 combinations. And I'll have my 1/4. So I'll have both up. Or both down. All right. Okay. Wait, that's the same thing. So make this one up and 1 down. All right. That's good. So this will be my 1/4 combinations. All right. That's not difficult. Let's go to synthesis. So for radical reactions, some of these syntheses require memorization. So check this out. If you're going to brominate, and you can brominate specifically at the allylic position with something called NBS. This is N-bromo succinimide. This part of the molecule is the succinimide structure, and it's an N-bromo bond. This chemical selectively just releases one bromine into a radical reaction. It's super cool. All right. So NBS is good. Notice that here you use a peroxide as a radical initiator. So you have a few examples of that here on the notes. So benzoyl peroxide, or which is that one, that's benzoyl peroxide. Or you can use tributyl peroxide. These guys will break homolytically in the presence of heat and will produce one radical that will initiate, your synthesis. So you make two of those. All right. Likewise here, these two electrons, upon heat, they will break up evenly homolytically, and you made that. And so that will be your radical precursor. There's another one called AIBN, which stands for iso-bis isobutyl nitrile. I have the mechanism how this breaks into. So basically, you're going to break this into these radicals here, and these two parts are going to make nitrogen gas, and the reaction is irreversible. And then you leave with two molecules of the radical and 1 mole of the nitrogen gas that escapes the solution, and it never comes back. All right, and so basically what I was saying there was, where is that? So you will make something like this, 2 times of that plus nitrogen gas. All right. So, yeah, let's go to this thing. All right. So, so this particular synthesis will make a vinyl halogen attachment. So check this out. So here you have a double bond. Remember, your vinyl groups is this. So if you put a bromine there, this is vinyl bromide. I'm sorry, no vinyl, my bad. Allylic. This is allylic. This is vinyl. So let's not get confused. I'm sorry. So allylic is similar to benzylic. So check this out. So we have benzylic. So I'll put my bromine here. So if I trace this as wind red, check this out. These are the same thing, similarly to that. All right. The allylic and the benzylic are very similar, and they are very reactive. And they're reactive because of resonance. And so you end up exclusively putting a bromine right there. That's the only product that you can make from this reaction. All right. Now, let's check out this other reaction. What do we get here? What will be the final product? What is this kind of reaction? You have an alcohol and you add hydrogen bromide. What type of reaction is that? Yeah, it's turning an alcohol.
Secondary,
SN1, exactly. Secondary is SN1, secondary alcohol. And you're going to exchange the OH by the bromine. Will it go to that carbon or to another carbon? Will it migrate to the carbocation? Will migrate to another carbon? it will migrate to the benzylic because the benzylic is the most reactive carbon in nature.
Are those not sp3s? They're not sp3s. No, they're not sp3s.
Yeah, these are sp3s. The final product is sp3. So you end up with a bromine right there. All right. So the initial gives you a plus here on the, and then you have a hydride shift to put the plus here on this carbon where the bromine is now. All right. What is this next reaction? So we have TS chloride, which is tosyl chloride, added to an alcohol. What is that? Protection of an alcohol, right? That puts a tosyl group there, which is a good leaving group. And the pyridine helps to grab the H from the water, from the OH. And then Ki, what does Ki do? SN2, this is a pure SN2 reaction. Second one, you will have K plus and iodine minus. Get rid of the K. And that kicks that one off. And there's no chiral center on that carbon, but there is chirality here on the previous one. So this chirality stays, and then you just simply put an iodine there. All right, so those are that. All right, let's see if you, this is a little bit review of formation of alkyl halides from alcohols. So what will be the precursor for this reaction? You have PBr3 and then it's down. The bromine ends up down. So what will be the precursor?
It would be the same thing, but an OH up.
Yeah. Same thing, but an OH up. Very good. Awesome. What about the next reaction? What is the precursor? From thionyl chloride. This is also, this reaction was an SN2. This reaction is also an SN2. We have gone through the mechanism. It's an OH where the chlorine is. All right. Yeah, that's it. Okay, any questions up to this point? All right, so I'm going to do the next problem here. Notice that this is a multi-step synthesis. In a multi-step synthesis, I always check what I had to start and what is new. So I have a 1, 2, 3, 4, and 5 carbons. 1, 2, 3, 4, 5, and I have a new carbon here, 6. I'm gonna put it in red. That's the new thing. I have put a carboxylic acid group there. Now, how can we go from 5 carbons to 6 carbons? We need to attach an extra carbon somehow. Before we can, even if we make an alcohol, if you were to like turn that double bond into an alcohol and you oxidize it, you still short 1 carbon. All right, you see that? So the best way to do, I mean, this would be a hard problem to solve on a paper test, but I would solve it going backwards. Some students might see it better, more beneficial to meet in the middle. You start with going backwards a little bit and then start going forward. So if I'm going to do this forward, I know I need to functionalize that double bond with an alcohol to start. Get that alcohol, turn it into an aldehyde, turn it into an alkyl halide, and then from the alkyl halide I can make a base, I can make a metal insertion with magnesium or lithium. Magnesium is easier. And then that becomes a base. Then I add a carbon that it could be nucleophile too. All right. So whenever I see a carboxylic acid group there, I know that this last reaction came from carbon dioxide in acid. All right. Um, so, in other words, let's say I have this reaction. So if I go, let's say if I have this reaction here, this reaction came from a precursor 1, 2, 3, 4, 5, 6 that looked like this. 1, 2, 3, 4, 5. Magnesium bromide plus carbon dioxide. So magnesium bromide is a 2 plus. Bromine is minus, so this carbon must be minus also. All right. So for magnesium, if you look at my magnesium bromide, if you look at my slides, I cancel that too because that's just a big spectator ion. This bond here is imaginary. This bond never happens because this is an ionic molecule. But for simplicity, OCHEM books write that bond like if it was covalent, which could be misleading at sometimes. All right, but I want you to be aware of that. So this goes in the tags, opens up, and now you form O minus here. You see it? And so on the second step, so going forward, you're adding carbon dioxide on the first step, which is dry ice. And then the second step is hydrogen. I'm sorry, you need a proton source, which is acid. And that is going to protonate. This is going to protonate that. And so you form final product. So that's how I can envision this last step. So the previous step to that is making so I'm here. So this is my last step. My previous step was adding magnesium in ether. So I go 1, 2, 3, 4, 5, and then I have a bromine here. Bromine, or let's say I have, why not bromine? That's fine. You can have a bromine, you can have an iodine there if you want. And going from here to here, you add magnesium in ether. All right. All right. So going more backwards, let me go backwards here. What's the precursor for this guy? An alcohol. So you have an alcohol there. And going forward, PBr3. All right. So PBr3 will come here. Or you can use PI3 if you want an iodine. Same thing happens. And then from here to here is starting material. How would you go from here to here? Hydroboration. Very good. So that will be almost there. Boron, THF, sodium hydroxide, and hydrogen peroxide. That's why it's 2 steps there. All right, so that's how you would do this. Not trivial. All right, but you can do it. All right, so the next set of questions here relates to lithium organocuprates. That's also a big section there. And lithium organocuprates are what is called soft nucleophiles. They would prefer adding 1/4 rather than 1/2. The hard nucleophiles go 1, 2. If you've seen the videos, which I know you've seen it. So what I'm talking about here is that the motion of the electrons go from the oxygen to this carbon right here shown as 4. So that's why it's called a 1,4 addition. If you were to attack, like is happening here, to this carbonyl, you will be doing a 1,2 addition using a hard nucleophile. All right. So let's work this backwards. I think this one is easier to work backwards. So if I want to get to this, I'll simply add a phenyl magnesium bromide or phenyl lithium will do the job here. I'm also going to put phenyl lithium here. So that means that this phenyl is negative. This whole thing is a spectator ion, and that's going to attack there. It's going to open up the carbonyl. It's going to put a negative sign there, right? That's an alkoxide. Then you have to quench that O minus, and you quench it with a soft acid. You need to use a soft acid because it's a tertiary. This will end up in a tertiary alcohol. If it's a tertiary alcohol that you're making, you need to use ammonium chloride. If you add H3O plus, you will make an elimination product. You will make, this case, it'll eliminate right there, and you don't want that. All right, so this H will protonate there, and then you make your 1,2 product. What about here on this side? To do a 1/4 addition, you use what is called a lithium organocuprate. So in this case, notice that what is new here is this piece. This is new. The rest I have there. I have those 4 carbons and the 2 methyl groups that I'm not counting. They're there. All right. So I'm going to add 1, 2, 3, 4. 1, 2, 3, 4 carbons. I'm adding 4 carbons. See, 1, 2, 3, 4 carbons. And so I need to make my bond long here outside the bracket, and that's my. This is my lithium butyl cuprate, also known as Gilman reagents. They are soft nucleophiles. They will attack exclusively on the 4th carbon or the 4th atom on the 1/4 addition. That's going to leave carbon 3 with a minus charge. So you have to quench it. You can quench it with acid, or if you want to put an alkyl group there, take advantage of that negative charge and put a methyl, an ethyl, whatever group you want to add there. All right, so what I'm saying is that this charge will come and attack in the 1/4, and it's going to push. It's actually going to push this way. But for your at your level, it's okay if you just put the negative charge there. You can see because the carbonyl is going to form back. Once you're advanced, you go to something like that looks like that. This is your enolate. We're going to study enolate next semester. But for now, let's just put the negative charge on the atom that says 3. And then that's going to put this group. And then if you quench it, now you can quench it with H3O plus. And that's going to put 1 H right there that you need. You have one already on the double bond, so you need another one to turn it into a CH2 group right there. That's how you would do this reaction. All right. All right. I think I have time for one quick question. It's good. All right. All right. We're done with chapter 12. And actually, we started chapter 11 already. So let's continue here in chapter 11. So for organometallic reactions, you will easily encounter these two examples I'm going to talk about. So check this out. If you have an alkyl halide, a boron compound, and palladium catalyst and a base, you are dealing with a reaction called the Suzuki reaction. All right. So in the Suzuki reaction, I want you to envision that this looks kind of like the handle of a motorcycle, right? Do you see it? That looks like a motorcycle. Here's the headlights, and then here's like the rear view mirrors here on the oxygens. And here is the tire of your motorcycle. All right? So if you see that combination of a boron compound, an alkyl halide, palladium, and base, hop on that motorcycle. All right? And say, this is the Suzuki reaction. So wherever the bromine is, and notice it's always going to favor the trans. The mechanism for this reaction is really long. You learn this in advanced OCHEM. These are loop mechanisms where you have addition and something called beta elimination. And that beta elimination usually produces a trans product. So basically what I want you to learn now is identifying the reaction and saying, okay, wherever this bromine is, I'm going to exchange it with the tire of my motorcycle. All right? And so we're going to end up with phenyl double bond. And here I have, my tire has 1, 2, 3 carbons. That's exactly what I'm going to put in there. 1, 2, 3 carbons. And that's the final product of my Suzuki reaction. All right. The next reaction that we're going to learn is the Heck reaction. Now, with a name like that, you know that a joke is coming, right? So, stay put. It's coming. All right. So, what is happening here in the Heck reaction? So, in the Heck reaction, you're going to see that we're going to lose a hydrogen, where the hydrogen is going to be exchanged by the alkyl group that was on the alkyl halide. All right? So, how do you recognize the Heck reaction? So, if you have a double bond, you'll need at least one hydrogen. And that hydrogen, preferably, is the trans. You're gonna check out for that trans hydrogen. In other words, if your final product was like this, you had a methyl group there. But you need at least one hydrogen to make the Heck reaction happen. And then the other portion of the molecule that you need is the alkyl halide. So in this case, it will be something like that with the bromine. So now you're going to take this alkyl part of the alkyl bromide and exchange it where the hydrogen is. So whenever you see a double bond with a hydrogen, an alkyl halide, palladium, and triethylamine looks like this, it's a base. You're gonna look at that H right there and say, hey, what the heck? That H will give you the Heck reaction. All right? That was the advertisement. All right? So notice that here, this is your new connection right there. That's the Heck reaction. Okay? All right. I have a few minutes just to go to retrosynthetic analysis. Okay, so notice that we have a starting material. First thing I do on the starting material is check for what is staying and for what is new. So here's the skeleton. So what is new is this methyl group is new. This chlorine is new. It took the place where the OH was, and this phenyl is also new. All right. So the question that I have here is that I envision both a 1,4 addition to a alpha beta unsaturated ketone, and then a 1,2 addition on the carbonyl. Why do we have to do the 1/4 addition before the 1,2? If you look at the previous example, what I'm saying here is, why do we need to do the 1/4 addition first? This one goes first before you do this kind. Second. If you destroy the carbonyl with the 1,2, the 1,4 will never exist. It will never happen. You see that? So we need to do that in order. All right? Never do the 1,2 and pretend that the 1,4 will automatically happen. Even though you know it, you need to add it in the right order. Oh, I forgot to complete the Suzuki. My bad. There is a cool reaction. So the Suzuki goes from here to there. But the precursor for this synthesis is phenyl with a triple bond. Now notice that if you have HBr and you add a peroxide, this makes an anti-Markovnikov addition. Putting the bromine, notice that it's going to put the bromine on the least substituted carbon. So the bromine ends up here and the H ends up here on this one. That's because it's a radical reaction. On a regular, without the peroxide, you will put the bromine here and the hydrogen here. All right? Because that goes Markovnikov. But for this particular example, HBr in peroxide gives you the bromine on the least substituted carbon. So be careful with that. Back to this one. And I only have 8 minutes. I think I should have enough time. All right, so let me delete this skeleton here for now. And so I'm going to go backwards. So I envision here that I did the 1,2 last. So I'll count my carbons. I have 1, 2, 3, 4, 5 in a phenyl. And I had, actually, before that, I'm going to exchange that chlorine with an oxygen. I know that from here to here, I can make that happen easily. And if I go back, what would be the precursor for this? Oh, and I have a methyl group here. The precursor for this molecule is what? So at this point, we're dealing with the 1,2 addition. So the precursor will be the carbonyl group. Carbonyl with a methyl group there. All right, we're almost there. Let's add ingredients to move forward. From start material, how do I get there? 2 steps. Lithium dimethyl cuprate. You need 2 molecules of the alkyl. All right, because copper is 2+ in this case. All right, and then you have the lithium. And then one of them, only one of these will attack in the 1/4. Then you want to protonate this carbon. You protonate it with acid, regular acid. That gives you that molecule. Then so this is your 1,2 addition. From here to here, what would you add? This is your 1,2 addition. What would you add there? You add a hard nucleophile. Phenyllithium or phenyl magnesium bromide. One of those two. Phenyl magnesium bromide is also known as a Grignard reagent. And then you're ending up with a tertiary alcohol, so you need to do a soft protonation. Use ammonium chloride. Really soft. It adds a proton and it doesn't really do anything to the reaction. It's not non-nucleophilic. And then going from a tertiary alcohol to a tertiary alkyl halide, what would you use? Cheapest hydrochloric acid. Use your cheapest material. Hydrochloric acid. This is a pure SN1 reaction. Very good. Aha. I have 4 minutes for the last one. Okay. So, this is kind of related to what we saw earlier. So we have 4 carbons here, and those 4 carbons here are there. This group, my carboxylic acid, is my new stuff here. So I'm going to see how I make it. So I need to extend that chain by 1 carbon. All right, I'm going to go from 4 carbons to 5. This has 5 carbons. All right, going backwards. I envision that I can put this carboxylic acid with carbon dioxide and acid with a metal insertion. So I'm going to insert magnesium in there. So here, I know that going forward, I can do carbon dioxide and acid. Acid will protonate this H. All right, going backwards a little bit, I had the alkyl halide here, where here I'm inserting the magnesium. So to insert the magnesium, I use magnesium and ether, and I make that. And then from here to here, oh shoot, I'm missing a carbon here. Like that, my bad. That's what we have. And from here to here, make the OH. What would you use to go from here to here? That would put the bromine here. It will make it PBr3 will make an SN2. All right, and how will you go from here to here? What would you do? Yeah, and what's the name of that reaction? Hydroboration. Yes, good job. 1. You use BH3THF and sodium hydroxide in the presence of hydrogen peroxide, H2O2. And that's it. Thank you. You guys did it. Any question? All right. I'm going to stop the recording.